Hello students, welcome to video lesson 7.1. We're going to do two sections in this video, 7.11, 7.12. The reason we're doing that is because 7.11, the first part, I think is very simple. We don't need to spend a lot of time on it. 7.12 is going to take us a little bit more time to work through a couple of problems. We're starting volume 2 of your textbook, so make sure that the one you have is the gray binding, not the blue binding. But notice that the page numbers basically continue on from chapter 6. So we're going to be dealing in the 300s, like page 318, 325, and so on. So we're starting volume 2, starting chapter 7. Today's discussion is going to be about functions, okay? It's going to be some tools that we may need as we move on to higher level math classes, whether it's calculus or any sort of other algebra class that's in college or anything else. So we're going to describe functions. We're going to review interval notation, things like that. So strap in and let's get started. So we're going to start with number 5, 7-5, and it's underneath the heading of concavity. So that's going to be our first new vocabulary today, is talking about concavity of a function or concavity of a graph. But we're going to start with a discussion of functions that are increasing and functions that are decreasing. Okay, now that part, I'm sort of skipping over the first few problems because I think we all sort of have an intuitive understanding of what it means for a function to be increasing, right? Basically, as the x value is increasing, the y value is increasing, right? Like a positive sloped graph. And a function that is decreasing, obviously, is the opposite. As x increases, y is decreasing. So those two ideas we're not going to discuss in terms of defining them, because I think we all already sort of have some understanding of that. But we do need to understand that when we describe a function, we're going to be asked to describe where it is increasing, where it is decreasing, and we're going to use interval notation to do that, okay? Interval notation is notation that looks something like this. Okay, it represents not a coordinate point, though with double parentheses it does look like a coordinate point. It actually represents a string of numbers, any value between this number and this number, okay? And the difference between an interval with parentheses and an interval with these squared off brackets is that with the squared off brackets, you are including the boundary points. If you're using parentheses, you're not including them. Okay, so we sort of think of it along the same lines as greater than or equal to versus just greater than. Okay, so this interval here would be this. If I can get the correct, here we go. So this would be like -5 less than x less than 5, right? There's no equal to here. So this interval does not include -5 and 5. It's just like -4.999999999 up to 4.9999999 and everything in between there, right? This one does include -5 and 5. So we call it an inclusive interval. So this would be -5 less than or equal to x less than or equal to 5, okay? And then one thing to note, we can use infinity and negative infinity as ends of our intervals, okay? If it's forever that direction, we'll use negative infinity or positive infinity, and those will never get square brackets because we can never actually include a number that is infinity, okay? It basically saying we can go as high as we want to, but there's sort of an upper bound that we can never reach, or a lower bound if we are going in the negative, so that's why it's always parentheses, okay? And then the other end, of course, in this case is +5, and that is inclusive. So this would be like negative infinity is less than x is less than or equal to 5. Okay, so when we write our descriptions of functions, we will say the function is increasing on maybe this interval, okay? Or the function is increasing on or decreasing on this interval, okay? For the most part, I think we will be using parentheses because I don't think we will be inclusive in any cases today. So we're going to focus on the parentheses intervals because we're not going to be including our boundary points, I don't believe. So if we look at a couple functions, and hopefully we can see these all right, we have the function here, y equals x squared. x squared. We have the function here, y equals the log of x. And then here we have y equals x to the third. Okay, and what we're going to try to do is we're going to try to describe these functions as increasing or decreasing on certain intervals. Okay, so for example, this function y equals x squared is decreasing on the interval from negative infinity up to 0. Okay, negative infinity up to 0, because everywhere in the negative, which would be, you know, this whole half of the graph, all of this stuff over here, as the x is going towards the positive, the y is coming down. So this is a decreasing function. And then when we get to 0, right, when we get to 0, notice that we turn around. We turn, we for just a second, we don't go anywhere, and then we go back up. So then we would say this function is increasing on the interval from 0 to positive infinity. Now, the reason that I'm using parentheses for both of these is because at the point 0, the function is actually neither increasing or decreasing. Okay, it technically has a slope of 0 when it hits the bottom. Okay, for just a second, it's like a horizontal line. All right, so we don't use a squared off brackets here because at that point 0, it is not increasing or decreasing. The same will be true when we talk about concavity. This particular function, log of x, we don't have anywhere where the function is decreasing, right? We don't have anywhere where the function is decreasing because nowhere as the x is getting positive is the y coming back down. Okay, this function actually doesn't even exist in the negative x values. So we just say that it is increasing on the interval, again, from 0 to positive infinity. Okay, increasing from 0 to positive infinity. Now, at 0 or at, you know, like 0.1, it's increasing very, very quickly. And then, you know, out here at x equals 8, it's increasing slower, but it is always increasing. Okay? And then y equals x to the third, this function is actually always increasing except for at one point. Okay? It's always increasing from the negative, like as far back in the negative as you want to go, as far down on the graph as you want to go. As x is going, you know, this direction, the y is always coming up. But right here at 0, it gets flat for just a second. So what we say is we say the function is increasing from negative infinity to 0 and from 0 to positive infinity. Okay, so it's basically saying everywhere except 0, the function is increasing. All right, so if you have multiple different intervals where the function is doing a certain thing, you can just connect them with the word and. This interval, and this interval, and this interval, and this interval, and so on. Okay? Now, we're going to come back to these three graphs in just a second, but we have to first get a sort of an understanding of concavity. All right? So there's two ways to describe a graph in terms of its concavity. And one of them is concave up, and the other one is concave down. Okay? Now, we can think of these in a lot of different ways. This is not the way your book describes concavity in the math notes box underneath problem 5. So if you like that idea better, that's fine, but I don't think it's very foolproof, okay? I don't think it's foolproof at all. So my understanding of concavity, before we get to a formal calculus definition later on in life, is the function is concave up if the slope of the line is increasing, if it is going up. So what I mean by that is the slope is either getting more and more positive, you know, sort of like an exponential growth function, right? That's one where it's flat to begin with, and then it gets a little steeper, a little more steep, right? So it's getting more positive, or the slope is getting less negative, okay? And that would be like an exponential decay graph, where the function is always decreasing, but it's decreasing at a slower and slower and slower rate, right? So the slope like back here might be like -7, but the slope here is like -0.5. Okay, so the function slope is getting less negative. It's coming down, but it's coming down less steep. Both of those are concave up because the slope of the line is going up. It's either getting less negative and closer to 0, or it's already surpassed 0 and it's going up and getting larger in the positive direction. Okay, that's concave up. Concave down is the opposite. The slope is going down. The slope is decreasing. So that can look like, you know, for example, a an upside down parabola, right? So an upside down parabola would look something like this, right? So let's say, you know, from this point up to the top, I am increasing my function, right? My value of y is increasing, but it's increasing at a slower and slower and slower rate as I get up there. So my slope is becoming less positive. I am increasing slower, okay? And then once I pass this line, now I start to decrease, and I'm actually decreasing faster and faster and faster as I continue on in the x direction, okay? My slope is becoming faster in the negative, and it's becoming slower in the positive, okay? Both of those together make concave down. What that means is the graph of this function, y equals negative x squared, is always concave down, all the time. Negative x squared, like an upside down parabola, is always concave down. Concave up, an example would be positive x squared, okay? A parabola is always concave up because its slope is, as it's decreasing, it's getting less negative, then it changes and it's getting more positive, okay? Both of those are concave up. So y equals x squared is an example that is always concave up. So if we go back to these three graphs here, and we, instead of talking about increasing and decreasing, we talk about concave up versus concave down. As I just mentioned, y equals x squared is a function that is always concave up. So I'm going to write concave up. And I'm going to say it's on the interval from negative infinity to positive infinity, meaning all the time, the whole time that the function exists, for any x value, it is concave up, because either the function is getting less negative or more positive. Okay, now for y equals log of x, this function, as I just mentioned, right when it starts at x equals 0, it's increasing extremely fast, right, going almost straight up. And then as it goes out, it's increasing slower and slower and slower. So what would we say about a function that is increasing slower and slower and slower and slower? Well, that slope, that increase is going down, which means it's concave down. So in this case, I'm going to say concave down, and it's also from 0 to infinity. The reason I don't go to negative infinity is because the function does not exist there. Okay, same with the increasing piece. Starts at 0, concave down, and it stays concave down the entire time, the whole time, no matter what. Now, this function x to the third is one where the concavity actually changes, okay, and it changes right here. Because this piece of the function, when x is negative, as x is going this way, the slope starts out very, very steeply positive, right? Steeply positive, and then as we get close to 0, it sort of flattens out, right? So the slope becomes smaller or less severe as we get close to 0. So from negative infinity up to 0, my slope is going from really steep to not quite so steep. So that's a slope that's going down or decreasing. So we would say this is concave down, okay? Concave down from negative infinity to 0, okay? But at 0, notice what happens. Now we start increasing, and we start out increasing just a little bit, but pretty quickly we get to be very steep again, right? So my function slope begins to go up in more positive, more steepness very quickly. So it becomes concave up once we hit 0. So what I say is concave up from then 0 up to infinity, okay? And where the concavity changes, in this case, x equals 0, is what we call a point of inflection. Okay, that is in your math notes box underneath number 5, so you'll want to write that one down. I think my understanding of concave up and down is easier to do on a graph than theirs, particularly because theirs doesn't always work, so I think it's kind of stupid. But the point of inflection is important. Where the concavity changes, make sure that you do take note of that. That is an x value where the concavity changes, all right? So we can describe functions by where are they increasing, where are they decreasing, where are they concave up, where are they concave down. That's what I'm asking you to do in number 7. Okay, so number 7 asks you to graph the function y equals x plus 1 over x. And I've graphed them for you here. And I want you to look at the graphs. I've marked a couple of points that are important for you because it's not super easy to always see sort of what these x values are. This is the point 1 in the x, 2 in the y, and this is -1, -2. So use this idea to find for me an interval or a couple of intervals where the function is increasing, where the function is decreasing, where the function is concave up, and where the function is concave down, okay? So you can do number 7 on your own, but do make sure that it is somewhere in the work that you submit, okay? The other way that we're going to describe functions in this section, and we're going to transition now to section 7.1.2, is a little bit less graphical, okay? But there is still sort of an application of graphing in it, but it's a little bit more algebraic, okay? And that is the idea of even and odd functions. Okay, so another way that we can describe function is by determining if those functions are even or odd or neither. And it is important to note that almost all functions are neither. Okay, but even and odd are very special, specific cases where functions can be described a little bit more fully by saying they're even or they're odd. Okay, so we're going to gain understanding of these two ideas, even functions, odd functions, by investigating a function for each, okay? So we're going to start with f of x equals x squared, y equals x squared. The graph of this function, of course, is a parabola. It looks something like this. So this function is number 17 in your book, 7-17 in section 7.1.2. So we're going to do all the parts of this question together and then do the same thing for number 19, okay? So letter A wants us to find outputs for the following inputs in this function. Okay, so they're going to give us x values. They want us to find y values. They want us to find f of 2, f of -2, f of 3, f of -3, f of 1.721, and f of -1.721. You'll find a pattern pretty quickly here. But if we plug some of these values into this function, it's a pretty easy function to evaluate. 2 goes in for x, so then f of 2 is 2 squared, which is 4. Right? -2 goes in for x, -2 squared, -2 times -2 makes 4. 3 goes in there, 3 squared is 9. -3 goes in there, -3 squared is 9. The next one I'm going to need a calculator for because I can't do 1.721 squared in my head. But on my calculator, I am told it is 2.961841, about 2.96. So this is approximately 2.96. And then f of -1.721. So if I do -1.721 squared, hey, look, I get 2.961841. So 2.96. All right, now, this function, we've just found all these different values. So we have these values that we just found for our function, right, in part A. Part B then says, do you see a pattern in the outputs? And explain what that pattern is. Well, hopefully we can all see the pattern, right? The pattern here is that the positive and negative inputs gave us the same output, okay? So that's what we need to say for letter B. Positive and negative inputs give the same output. So it doesn't matter, as long as it's a 2, it doesn't matter if it's +2 or -2, it gives me the same answer. It doesn't matter if it's +3 or -3, it gives me the same answer. It doesn't matter if it's positive 100,000 or negative 100,000, it's going to give me the same answer, okay? So these, whoops, I doubled my R there. This pattern is basically our definition for an even function, okay? So letter C, as we just get through these last few questions, says input a and -a for the function a squared. So we get, if we put in f of -a, that would be equal to a squared. And if we put in f of +a, we would also get a squared. So it doesn't matter if we have negative a or positive a, it's the same thing, okay? So then letter D, they want us to use the graph or what we just wrote to write an equation that relates f of positive a and f of negative a. And this is the key right here, the key piece of a function being an even function. Okay, an even function needs f of positive a to be equal to f of negative a. F of positive a equal to f of negative a. Okay, no matter what you plug in, positive or negative, as long as it's the same absolute value, you get the same answer from the function. Okay, letter E then says describe the symmetry of the graph. Because if we look at the graph, this is another way to identify even functions, and that is this graph has a line of symmetry, right? If we folded it over, it would be 100% the same if we fold it over the y-axis. So we would say reflection, right, which means to flip it over, reflection over the y-axis. Okay, and that is an even function. An even function has to have a reflective symmetry or a foldable symmetry over the y-axis, and it has to have the positive and negative inputs give you the same output. Okay, that is how we identify an even function. Okay, so an even function gives the same output for positive or negative inputs. And again, in parentheses, also has reflective symmetry over the y-axis. Okay, those are the two sort of distinguishing characteristics of even functions. Even if just one of them is true, you know that that thing is an even function, okay? Because they really mean the same thing. One is algebraic, one is on the graph, okay? That's an even function. Positive, negative gives you exactly the same answer, okay? Now, if we transition then to looking at f of x equals x to the third power, so not x squared, but x to the third power, that function on its graph looks something like this. It does that, and then it does that, right? This is number 19 now in chapter 7. They want us to basically do the same steps here, okay? The same things, go through the same steps with this function and see, is it similar idea? Is it different? How is it different? We should all be okay with the idea of this is going to be an odd function. We can see sort of what are the characteristics of an odd function. So if we, for part A, if we plug in all these values again, let's say -2, let's see, -2 to the third power is -2 times -2 times -2 makes -8. F of +2 is going to be +8, right? 2 times 2 times 2 is 8. Then they want us to do it for the 3's. F of -3 is -3 times -3 is 9 times -3 is -27. F of +3, 3 times 3 is 9 times 3 is 27. And then, again, I'm going to need my calculator for the decimals. 1.721 to the third power gives me 5.097. So I would say F of 1.721 is 5.1 approximately, right? 0.097 is about 0.1. And then I'll do the same thing with the negative. Negative 1.721 to the third power. This one I'm going to put in parentheses, and I get negative 5.097. So I get negative the same number, approximately 5.1. So now the question is, do you see a pattern in these outputs for letter B? Well, the pattern is I'm basically getting the same answer, right? Except I'm getting one that's negative and one that's positive. So if I put in a positive and negative version of the same number, +2, -2, +3, -3, +5, -5, I'm going to get positive and negative versions of the same answer, okay? So in this case, we would say, yeah. So here's what we'll say. We'll say changing the sign of the input changes the sign of the output, right? Changing the input from positive to negative or from negative to positive is going to flip the sign on the output value that you get. Now, in terms of sort of what that looks like in letter D when they want us to compare f of a and f of negative a, where they're just sort of random positive and negative of the same number, what we can say is f of negative a, if I put in a negative, I'm going to get exactly what I would get if I put in a positive, except it's going to be the opposite sign, so I'll put a negative sign in front. So what we read that as f of negative a is equal to negative f of a. So changing the sign on the input also changes the sign on the output, okay? So letter C says, if you input a and negative a for the function, what's true about the outputs? Well, they're the same, I'll say same absolute value. Different signs. Okay, so that's algebraically what is true about odd functions. If you put in a positive and negative of the same number into the function, you should get a positive and negative version of the same number as outputs, okay? Now, in this particular case, we got negatives when we put in negatives and we got positives when we put in positives, but that's not always the case, okay? That's not always true. And then letter E, again, is talking to us, asking us about the symmetry of the graph. Now, it's important to know the symmetry here is not a flip, okay? We're not drawing a line and flipping it over or folding it over, okay? What we need to recognize is this piece right here, okay? If I were to rotate it around the 0, 0 point, if I take this piece and I rotate it around the 0, 0 point, like rotate it this way, it becomes the other piece. Okay, so there is what we call rotational symmetry. If we turn it back like a volume dial, we should get the other piece as well, okay? So there's rotational symmetry around the origin, and particularly it's 180-degree rotation. So we'll say 180-degree rotation around the origin. Okay, that has to be true for an odd function as well, okay? So two things, two representations of the same idea, okay? Algebraically, if you change the sign on the input, you will change the sign on the output, okay? Positive, negative will result in positive and negative with the same number. In terms of on the graph, we see a symmetry of rotating the graph 180 degrees and it will pop right back to what it was before, okay? So again, odd functions, they have rotational symmetry around the origin. And I'll put in parentheses here, 180 degrees. And f of negative a has to be equal to negative f of a, okay? So that's the two things the two distinguishing characteristics of odd functions, okay? So again, as I mentioned before, most functions are neither one of these things, but we can describe a function as even or odd, and when we can do that, it is helpful, okay? So I'm gonna just show you a couple, like maybe one example of a function, and we're gonna check and see, is the function even or odd? And I'm gonna do it algebraically, okay, without looking at the graph, but you could do it that way as well. Let's say we have the function f of x is equal to 2x squared plus 4, okay? 2x squared plus 4. If I want to check and see if this is even or odd, all I have to do is I have to plug in input values, and I have to plug in a positive and a negative of the same absolute value. So for example, I can find f of well, here's what we should probably do actually. To prove it, we should do it with a variable. Okay, so I'm going to plug in f of a, right? And that's going to be 2 times whatever a is squared plus 4, right? So a squared is just a squared. So this says 2 times a squared plus 4, right? So when I plug a in, it just really replaces the x with an a. But if I plug negative a in, what happens? Negative a, so this says 2 times parentheses negative a squared plus 4. So what is negative a squared? What happens when I take a negative number, a negative value, and I square it? Well, the negative value squared basically flips it to positive, right? Because negative times negative is going to be positive, right? So we can think of that as negative a times negative a. Negative times negative is positive. A times a is a squared. So this becomes a squared times 2 plus 4. Okay, so notice what I got when I plugged in negative a. That is 100% the same as what I got when I plugged in positive a, right? So because these two values are exactly the same, this is an even function because f of positive a was equal to f of negative a, okay? Now, if you want to see an example of something where it's neither, let's just use a similar sort of function, but instead of 2x plus 4, or sorry, 2x squared plus 4, let's do 2x squared plus 4x, okay? So now let's plug in f of a. Well, again, plugging in f of a is just going to change, excuse me, should be g of a now. G of a is just going to change the x's to a's because a squared is a squared. 2 times that plus 4 times a is 4 times a, 4a, right? So I get this. Now, if I plug in negative a, what happens to the function when I do that? Well, the first part is going to be 2 times negative a squared plus 4 times, instead of x, I'm going to put negative a. So what happens here? Negative a squared is simply a squared, right? Multiplied by 2, well, that's 2a squared. And then this 4 times a negative a is negative 4a. So it says this now, 2a squared plus negative 4a, well, that's like minus 4a. So I want you to look at this. Are these two things the same? Are they the same? Nope, they are not the same, okay? So this function is not even. I guarantee it's not even because g of a and g of negative a are not the same expression or same equation. So the next question is it odd? Is this an odd function? Well, in order for that to be true, I should be able to put a negative sign in front of g of a and have it be this. So if I put a negative sign in front of this thing, 2a squared plus 4a, do I get this? Negative, all of this stuff is equal to this. Well, no, because I'd have to distribute the negative to both pieces, right? So I would really get negative 2a squared minus 4a. So in this case, is this, when I put the negative sign in front of g of a, do I get g of negative a? Are these exactly the same thing? No, because 2a squared is not the same as negative 2a squared. So this is not odd, and I just proved a second ago it's not even, so this is neither. And that's what happens most of the time when you do this, okay? It's just certain specific situations. We can find a function and describe it as even if the negative a and positive a plugged in give me the same thing, or odd if the negative a and positive a give me the same thing, but one's just every sign is flipped, okay? If you have questions about describing functions, increasing, decreasing, concave up, concave down, even or odd, please reach out to me, let me know. Be happy to help with your practice problems. Otherwise, that's all I have for you, and we'll talk to you soon.